Hey guys, today I'm going to introduce the canonical endomorphism associated with the matrix in order to interpret 2x2 or 3x3 matrices geometrically and to prove some important properties of matrices.
Well, let's define this endomorphism considering a matrix whose components are A11 up until ANN, and let's associate with this matrix an endomorphism that we will call F. Let's define this endomorphism by characterizing its behavior on the canonical basis. Well, the canonical basis is the basis composed of the vectors whose components are 0 except for the ith one, which is 1. We'll call this vector EI. Well, F is defined by this equality. F of the ith canonical vector is equal to the ith column of the matrix A, but in vector form. For example, here, F of E1 must be, by definition of F, must be the vector A11 up until AN1. So, it must be, by definition, A11 0, 0, 0, 0 plus etc. plus 0, 0, 0, 0 AN1, which is the vector A11 up until AN1 if we sum up all the terms here. So that's how it is defined. Now let's prove an essential property. If F is the canonical endomorphism associated with the matrix A, then A times X is equal to Y, where X and Y are column vectors whose components are respectively X1 up until Xn and Y1 up until Yn. So this is X and this is Y. So this equality is true if and only if F of the vector X, whose components are the same as the components of the column vector X, is equal to
The vector whose components are the same as the column vector Y.
Well, let's prove the first implication. Let's suppose that A times X is equal to Y, and let's prove that F of X is equal to small y. Let's rewrite F of X in order to prove that it's equal to Y. F of X is equal to F of the sum for L running from 1 to N of XL, EL, by definition of a vector in the basis. But by assumption, F of EL is equal to the sum for K running from 1 to N of AKL, EK. So let's rewrite this vector. So we end up with this equality, but by assumption, A times X is equal to Y. So, in particular, let's choose the ith line of the matrix A. In particular, the sum for K running from 1 to N of A I K times XK is equal to the yth line of the column vector Y, that is to say, just a scalar, a component, yi. Alright? So, by assumption, we have this equality. And we want to prove that f of x is equal to y. So obviously we'll have to use this equality to prove that this vector is equal to the vector y. Here we sum on the columns of the matrix A. Here the running index is k. And here we sum on the lines of the matrix A, but there's another summation. And we can interchange the summations because we do not sum up until infinity. So we end up with this equality, and you might recognize with yk here. The running index here is L instead of k. And the line we've picked up is here k instead of I. So this is equal to yk. And then we have that f of x is equal to the sum for k between 1 and n of yk ek. That is to say, f of x is equal to 1, 0, 0, 0 plus, etc., plus 0, 0, 0, 0, yn. That is to say, f of x is equal to y1, y2, etc., up until yn. So, f of x is equal to y. Let's prove the reciprocal. Let's suppose that f of the vector x is equal to the vector y. Then let's prove that a times x is equal to y. We just have to prove, in fact, that for all the lines of the matrix A, this line times the column vector x is equal to the same line of the column vector y, that is to say, just a scalar, a coefficient. Well, if we name the line of the matrix A Li, we just have to prove that for all I between 1 and n, Li times x, which is a scalar, is equal to yi. Well, we've supposed that f of x is equal to y. Now let's prove the implication. Well, we can rewrite x as the sum for L running from 1 to n of xl el, by definition of a vector and a basis. Then, by definition of an endomorphism, it is linear, so we can rewrite this as the sum for L running from 1 to n of xl f of el. But, by definition, f of el, by definition of the canonical endomorphism, of course, f of el is equal to the sum of the ak l ek. So let's use that definition. So we can rewrite f of x as this vector, and likewise we can interchange the summations to make this expression appear. And you can see that this is by definition of the matrix product, the product of the kth line of the matrix A and the column vector x. Well, this is the kth line of the matrix A, and this is the column vector x. So here we have x1 times ak1 plus x2 times ak2, etc., up until xn times akn. And here, by definition of the matrix product, we have the same thing. ak1 times x1 plus etc. up until plus akn times xn. So this is the line k times the column vector x, right? This is a scalar, huh? So f of x is equal to y implies that the coordinates of this vector are the same as the coordinates of the vector y. And by unicity of the coordinates of the vector in the basis, for all k between 1 and n, lk times x is equal to yk. And we've proven what we wanted to prove. Well, by rewriting y in the canonical basis, we have the following equality, that L1 times x minus y1 up until Ln times x minus yn is equal to the vector 0. So, for all I between 1 and n, Li times x is equal to yi. So we've proven that A times x is equal to the column vector y. Well, hope you enjoyed this video. Thanks for watching, and ciao ciao!